Welcome back, guys, to the final video in this lecture mini-series. We're going to round out this mini-series by looking at a handful of periodic trends. Now that we've used quantum theory to understand the concept of an orbital, the concept of an electron configuration, and we've gained an appreciation for why the periodic table is ordered the way it is, we're now going to build upon that and look at some other trends that show up in terms of related behavior in the different groupings and arrangements of atoms in that periodic table. So to recap what we've learned so far, we've introduced this concept of valence electrons. Basically, these electrons that are in that outermost highest energy orbital, and core electrons are then all those electrons that are inside that highest energy outermost orbital. Okay, so now we're going to use that concept to essentially start to uncover our first periodic trend that we're going to talk about, namely the trends in the radius or the size of atoms as they're arranged in the periodic table. So to do this, we're going to have to introduce related topics known as nuclear shielding and effective nuclear charge. Okay, so nuclear shielding is basically the result of electron-electron repulsion. If we look at our little example here, and we have these little electrons distributed in this cloud of probability, 1s, it's spherically symmetric cloud of probability around that lithium nucleus in this case, then that outermost valence electron in that s orbital isn't just looking at a bare nucleus, it's looking at a positively charged nucleus through the screen of these intervening electron clouds. And so the result then is that the effective charge that this outermost electron feels is not the 3+, but it's the 3+ charge of the nucleus reduced by the charge in this intervening region. Now notice, this is an approximation. Just because there's 2 electrons here does not mean that this outermost electron only experiences 3 minus 2 or plus 1, right? This is approximate. These electrons do not perfectly screen the charge. This outermost electron, of course, resides in an orbital, and that, even though it's a larger orbital, it still penetrates this core region. So this is very much an approximation. But the point is, and really the take-home message, is that these outermost electrons are going to be not quite as attracted to the nucleus as they would be otherwise. And this has some very important implications. So if we compare boron and nitrogen and draw out some sort of simplified view of these orbital models, then we can see that, so for boron, we're both second row elements. So our outermost shell is going to be n equals 2 in both cases. For boron, we have a total of 5 electrons. So we're going to have 2 core electrons in a 1s orbital. Then we're going to have 2 more in a 2s, and then another electron in a 2p orbital. Okay, and so all of these, in this case 3 n equals 2 electrons, are going to be seeing a nuclear charge that is screened by 2 1s core electrons. Now move to the right on the periodic table a couple steps and come over here to nitrogen. And of course, what we're doing in this case is increasing the nuclear charge and increasing the number of electrons in that outermost n equals 2 shell. So the same number of core electrons are present in both, but now we have a greater number of valence electrons. But because we have the same number of core electrons and a larger nuclear charge, what ends up happening in the case of nitrogen here is these outermost electrons in the n equals 2 shell are experiencing a greater effective nuclear charge, because now you have a charge of +7 in here that's screened by 2 electrons versus a charge of +5 that has the same screening of 2 electrons. So in this case, we've got a greater effective nuclear charge. And so if there's a greater effective nuclear charge, then those outermost electrons are going to be pulled in, and their corresponding probability distributions are going to be shifted closer towards that nucleus. So as a result, we have our first periodic trend. As you move across a given row in that periodic table, right, from left to right, then the size or the atomic radius is going to decrease. All right, so we're going to see a decreased size in atoms. Now, if you move down the periodic table, well, we already explored this in the previous lecture when we looked at the radial distribution functions in our CDF interface. When you knock out or you lock down, say, a 95% probability region for finding these electrons, and you compare the relative distributions for a 1s, 2s, 3s, and a 4s, right, we can see that in order to capture 95% of those events of finding the electron, you go out a little beyond 3 Bohr radii for a 1s, or beyond a 10 Bohr radii for a 2s, beyond 20 for a 3s, and getting close to 40 Bohr radii for a 4s. In other words, as n gets bigger, as you go down the periodic table, right, then the atoms increase in size. So we get larger atoms. So to sum this up, we can look at the radii, in this case given to us in picometers, for a subset of the elements on the periodic table, and we can see that as you go down that column, we're seeing larger and larger radii, and in general, as you move left to right, you're seeing smaller and smaller radius. Now, there are some instances where this general trend does not hold. And I'm not going to hold you guys accountable from a testing standpoint for any of those exceptions. I basically just want you to remember those general trends of increasing radius as you go down and decreasing radius as you move left to right, and being able to understand how nuclear shielding allows us to understand this trend, the decreasing radius left to right, and how the relative size dependence with increasing quantum numbers allows us to predict the trend as you move down a column. And if we plot this out so that we can monitor these trends a little bit more effectively, then some of these anomalies show up a little bit more. And so we can see that in the region of transition elements, I'll just make a note here. Again, I don't want you to have to try to remember all little squiggles, ups and downs. But notice that when you're moving across the d block elements, those transition metal elements, you are adding electrons to d orbitals, which have a constant number of valence s electrons. And so as a result, the atomic radius doesn't change substantially, right? Because remember that a mismatch in the ordering. The d orbitals are actually lower in energy, relative to the s orbital. The underlying s orbital is lower in energy than the d. So the d orbitals are lagging behind by 1 quantum number. Okay, so our outermost s, the largest principal quantum number s, is constant, so we get these regions of relatively stable radii. All right, so before we move on from this, let's point out one other implication related to the size of ions. So if you form a cation, you're of course losing your outermost electron. So it's not surprising that when you form a cation, the cation is going to be smaller than the corresponding neutral atom. But what might be surprising is how much smaller it is. And again, we can understand the relative magnitude that I have illustrated here for the group 1, 2, and then going over to 3A as well. we see that there's a dramatic reduction in size, and this comes down to basically the larger effective nuclear charge that these new outermost electrons see. Because remember, if you have a lithium atom, you have a 1s2, 2s1. And so your valence electrons are a 2s orbital. So by forming the lithium plus, you have an electron configuration that's the same as helium, but now you have a whole nother charge. And so there's a very dramatic change then in terms of the relative attraction between the outermost electrons and that nucleus. And conversely, if we form an ion, or we increase the number of electrons, then we are putting more electrons into higher energy or larger orbitals. So it's, but once again, probably not surprising to see that the radius of ions increase. And of course, they will then be experiencing a smaller effective nuclear charge in many cases, simply because you've got more electrons in that outermost shell. And those electrons in that outermost shell are, of course, both negatively charged and going to be repelling one another, and of course, giving rise to these increase in radius. Now, a really cool application of these ions, it comes about in biological systems that you will probably study, later on in your coursework, where you'll see these really fascinating looking protein structures, which I'm showing here by all these little curlicue looking things, embedded in the membrane of a cell. And these proteins here, embedded in the membrane, are what we call ion transport proteins. And these huge, massive structures are designed to be able to selectively identify one particular anion or cation from another, and only allow those specific ions, for example, chlorine, to pass, but exclude all the other ions. And so this size, these size trends are one of the main ways in which these proteins, function in terms of excluding ions that are the incorrect size. Charge, of course, is the other characteristic that they use then to help figure out which ion gets through and which ones don't. So to sum up the trends in atomic radii, in general, radius decreases moving left to right, increases moving down the periodic table, cations are smaller, and anions are larger. All right, on to our next periodic trend. In this one, we're going to be looking at a concept called ionization energy. So the ionization energy refers to the energy required to ionize an atom or a molecule. But for right now, we're going to focus in on atoms, and we're going to talk about the so-called first ionization energy, which is the energy required to remove an electron from a neutral atom in the gas state. So for example, if we look at sodium, sodium is sitting here with 11 electrons, with an outermost electron here, and 3s1, right, a 3s orbital. And if we are going to remove that outermost electron, we are going to be left with a sodium ion, which of course has the same electron configuration as neon. And we can measure the amount of energy that's required to rip this electron away from that sodium atom. And it turns out in this case that number comes down to 496 kilojoules per mole. Okay, so when we're asking that question, from which orbital does a sodium lose its electron, remember the guiding principle that we use in building up electron configurations. We always put electrons in the lowest possible orbital. Okay, so it is possible to remove a core electron, and there are different forms, different types of experiments that involve the removal of core electrons. But the vast majority of experiments, and all the ones that we're going to be caring about for this class, are actually removing that outermost valence electron. And that's going to be the trend that we're looking at here. So we're removing that outermost electron in a 3s orbital. Okay, now I have a question for you. If it requires, as I told you on the previous slide, 496 kilojoules of energy, kilojoules per mole of energy to remove the first electron from our sodium atom, how much energy would you predict it needing to remove a second electron, right? Move an electron from this sodium plus ion. Do you think it's going to be more than the 496? Exactly the same as the 496 or less? Go ahead and pause the video for a second and come up with an answer. Okay, well the answer, hopefully you've predicted, is going to be greater than the 496. It's going to be harder to remove another electron. And you can think about it in terms of basic electrostatics. If I've got a sodium plus atom, now we've got a positive charge, and so that positively charged ion is going to be more attracted to negative charges. So removing another electron, you're now removing something negative from something that is positive, and even more positive, wanting to hang on to that electron to a greater degree. And we quantify this removal of a second electron using the so-called second ionization energy. So the energy to remove the second electron from an atom is called the second ionization energy, and we will see that it is typically much larger than the first. So if we go back to our sodium example, we'll see that it actually requires 4,560 kilojoules per mole of energy to remove a second electron from that sodium plus cation. All right, so if we plot out the ionization energy as a function of atomic number, we see a number of important trends that come out. First off, if you follow, for example, the noble gases or any given column on the periodic table, we will find that there is a general decrease in ionization energy. And what that means is that ions further, or electrons further from the nucleus are basically held less tightly. And this makes sense. We know that electrons further from the nucleus, well, they're not as close to that positive nuclear charge, therefore they're not going to be as attracted to it, and it's going to be easier to kick them out. Now if you zoom in here and you look as you move across a row, we're actually seeing an increase in ionization energy. So to map this back onto the periodic table, the general trend as you move from left to right is an increase in ionization energy. It becomes harder to remove electrons. And again, that goes right back to that greater effective nuclear charge concept that we talked about before. And as you go down that periodic table to larger and larger atoms, electrons that are further and further away from the nucleus, well, they're easier to be lost, so you get a decreasing ionization energy as you move down. All right, now we're going to talk about our third periodic trend, which is related to the concept of electron affinity. So electron affinity of an atom is the energy associated with the gaining of an electron by the atom in the gaseous state. So the electron affinity for chlorine here would be the energy associated with taking a neutral chlorine atom in the gas phase and adding on a single electron to form Cl-. Right? Turns out that the electron affinity is, for chlorine on the order of minus 349 kilojoules per mole. So typically, we're going to see negative values for these electron affinities, but that's not always the case. There's a number of exceptions. So for example, the entire column of noble gases will have positive electron affinities. They simply don't want the electrons. But fluorine and the rest of the halogens have a relatively high affinity for a different an additional electron, followed by oxygen, and so on and so forth. So we can see that the affinity for electrons is typically increasing. It'll increase as you go up the periodic table, and it will increase as you move from left to right. Again, many exceptions, but I just want you to remember those broad overarching trends. And then lastly, for our final periodic trend is that a discussion of metallic character. Basically, metallic character we know corresponds to those properties of conductivity, the metallic luster, and all that stuff we've talked about earlier in the course. And what we will see is that metallic character generally increases as you go down the periodic table and decreases from left to right. So this guy down here is the most metallic and then least metallic up here in the top right. So to sum all of this up, we have a handful of trends here that I want you to remember. Again, just the broad trend. Atomic radius is getting larger as you go down and larger as you go from right to left, right? If you look at the ionization energy and electron affinity, run parallel to one another. You have a greater affinity for electrons as you move from left to right and from bottom to top. And then metallic character increases in the top right and is lowest on the top left.